Okay, so in terms of the rest of this morning's session, I am now going to hand over to Max Yan, who's going to chair our first session. So thank you very much, and I'll hand over to Max.
Thank you, Andy. Hi, everyone. Welcome to the transport and heating session. So just a reminder, if you haven't already, please keep your video and audio feeds on mute and use the chat box to ask questions, as you can see has already been done. So I'll announce verbally when there's 5 minutes remaining to the speakers. And please let me first introduce the first speaker, Rachel Lee, from our own Energy Storage CDT at the University of Sheffield, who will be presenting her work on EV ownership and charging profiles.
Okay, thanks, Max. Can everyone hear me okay?
Yes, I can.
Okay, yeah, thanks for the introduction, Max. So I'm going to talk about some social and locational impacts on EV ownership and charging profiles. The usual thanks to my supervisors, Sol and Rachel Rothman, and to Drax and EPSRC for funding. If I can make this work on, yeah. So my shorter title for my PhD is Electric Vehicles, How Far Can We Go? So my kind of overall objective, just as a refresh on that, is to kind of explore the impacts of policies on adoption and social equity, and try and look at what policies and measures are needed to make the transition to electric mobility equitable. To understand how EV adoption impacts on demands in different parts of the network, and to try and establish some kind of view based on those things of the practical contribution that vehicle to grid might make to balancing UK grid systems. So the way I'm doing that is that I've been building an agent-based model. So that's the kind of model where there are lots of individual actors within it. In my case, the main actors are car owners and cars, but there are also other actors such as media and governments and car manufacturers and so on. My car owners operate by using a kind of consummate model of human behaviour, where they sit in different states, and you can see this person here is happy driving their car, and they're sitting in a state of high satisfaction and low uncertainty, by which I mean they're doing similar things to their peers and they're happy state of mind. So they keep repeating actions. What could happen, for example, is that their car might start having reliability problems, and that could actually result in two different scenarios. One is that they become unsatisfied with their car because it's breaking down frequently. But another possibility is that they might just be looking at their peers and seeing that their car isn't as reliable as their peers' cars, so they might become less certain. They might feel that they're not doing as well as their peers. So that person becomes unhappy. They start to look at what their peers are doing in terms of their cars, and that could be friends, neighbours, work, social media friends, that kind of thing. They look at what government policies are in place, and they may take account of advertising from car manufacturers. And they make a decision by looking at the car market based on all those factors and choose a car. And let's imagine that they choose to replace that car with an electric car. They don't have to in the model, and they're happy. And the next phase of that might then be that in the case of an electric car, they could look at what type of charging contract they have, with an ultimate aim in my modelling of them being able to work out what might be available for grid services and things. I'm not going to talk about that part today. I'm going to focus on the sort of more the social side of it, social equity side of it. But I thought I'd start just by saying, can this kind of modelling be effective? And I've just produced a couple of charts there that from a paper that's currently under review. And they show the way that I've kind of tried to validate this model is to run the model from 2003 by setting it up with the car market as it was then, and seeing what happens up until today. And the chart at the top right shows the model outputs in solid line and the statistics from Driver Vehicle Licensing Agency in dotted lines for the sort of switch that we saw from petrol to diesel. And you can see that the model does quite well. Diverges a bit at the end. That's partly because of Dieselgate, which I haven't tried to model there. And it's partly because it over forecasts in that version the shift to hybrids and battery cars. And it partly does that, as the bottom chart shows, because of brand loyalty. And I've just included this as a kind of demonstration of human behavior and the fact that rational decisions are not really the way the market always works. So that the chart there shows the model prediction without loyalty being included in it, and it shows quite a large uptake of hybrid vehicles. And I've used hybrid vehicles because there's only a couple of brands available at the start. For about 15 years, in fact, there were only Toyota and Honda cars. And if you take brand loyalty into account, you can see the bottom line there, solid line against the DVLA statistics, and it improves it substantially. So that's kind of a very clear example of how the way that people behave might affect adoption. So I'm going to move on to that to talk about the main subject of the paper. And I'm going to talk quite a bit about some of the area classifications that are used in something called the National Travel Survey, which I use extensively. But I wanted to start by just plotting those classifications, which are along the bottom there, rural residents to the hard pressed, that you can see a kind of socio-economic groups in a sense, but in the NTS, they're actually based on Office for National Statistics area classification. So they're more a kind of geography-based classification than specifically the people in the areas, and you get some overlap. So although you can see that, I hope you can see my cursor, but at the hard pressed end there, we've got, we probably expect those people to have lower incomes, and indeed they do on the whole have lower incomes. These darker areas are the lowest quintile income band, but there are also a few, in fact nearly 10% of people who fall into the hard pressed locale who actually have very high incomes. And that can distort the results when you present them there, because you do have some high income people, but you can see that there is a trend for those groups to have lower income, whereas suburbanites here, for example, tend to have medium to higher incomes. So how does it look when we try to forecast the future for battery uptake, battery electric car uptake? And there are two examples here. One where all we do is keep the existing battery electric vehicles that are in the market at their current prices. And you can see that there's not a huge leap in adoption. They're too expensive, basically. But you see that rural residents and suburbanites kind of lead the pack there, really. And there's possible explanations that they've got higher incomes, of course. It could be that they've got access to home charging. It could be that simply they do more miles, and therefore those who do make a rational total cost of ownership type of decision might be more likely to adopt battery cars there. If we then sort of modify the model and add battery cars that have a 300-mile range and a price parity with fossil fuel cars in 2025, and that's not completely unreasonable. There are lots of forecasts that suggest we will be at price parity in 2025. Then you see quite a different adoption, and you see still that the same groups lead it, but you start to see this gap opening up between the rural residents and the suburbanites there, and our hard-pressed and constrained city groups at the bottom. And that's partly because these groups are actually kind of waiting for used electric cars to become available. And that sort of happens as these kind of wealthier groups upgrade, typically to longer range cars. So does household income affect it? These plots here are trying to show that it does. So they show on this depth scale the decade that the first EV in a household is purchased. And along here we've got the income quintiles, so the most highly paid at this end and the least highly paid at this end. And you can see therefore that from these charts that certainly in this case where we have expensive cars, the income is clearly a driver of early adoption. It's predominantly the people with lots of money that are buying electric cars, and that exists through the 2020s and continues into the 2030s even. But even in this scenario, over 40% of households own one battery car by 2038. But interestingly, adoption by individuals is only 20%. And you get that difference because of this sort of second car phenomenon, which I'll talk about in a bit, where that lack of range in early BEVs means that they're often adopted as a second car. And then here, when we've got price parity, we see a slightly different trend. We still see early adoption by more wealthy people, but by the time we get to the 2030s, actually that's evened out. And we see adoption, first adoption across all income groups, and that is partly used electric vehicles becoming available, and also actually because a lot of the higher income groups have already bought their first EV by the 2030s. So you can sort of see from this that it's predominantly the rich that benefit from capital cost subsidies, but we kind of have to be careful there because they are also enabling cost reductions by buying cars, and they create a used car market for others. So what about this second car importance? So if we look at the current models on the left, what the chart here is showing the percentage of battery car owners owning households who only own the BEV. So, and we see that when you've only got these limited range cars, even by 2030, only about 20% of cars of households only own a battery vehicle with these short ranges. But when we increase the range up to this 300-mile range, then that increases dramatically by 2030. So this is kind of confirming really that access to a second car is important, certainly for early adoption when ranges aren't quite so good. And it's generally going to be the more affluent households who have access to multiple vehicles. So you could argue that's another barrier to early adoption. Interestingly, though, home charging isn't quite as critical as you might think. So here, the blue bars are showing the percentage of each house, of each of those groups there that might have access to home charging. And that's based on some English Housing Survey data, which says which the proportion of each of those groups that have off-street parking or dedicated off-street parking. So you can see from that, if you look at the darker green bands, that there's a bit of a trend for early adopters to have home chargers, because the dark green tends to be a little bit higher than the blue. So you've got a higher proportion of BEV households with chargers than households that have access to charging. But it's not actually that significant. And the cosmopolitan and ethnicity central groups there, although there's only 3 adopters between them in 2020, none of those 3 actually have home chargers. So it isn't essential. And actually, I think that's kind of reinforced by anecdotal evidence from social media groups that I look at and discussion with EV owners. There's a surprising number who don't have access to home charging. And then if we move on to looking at the electricity demand impacts, I've shown in the chart here a sort of subset of those groups, and it shows the mean diversified household charging load during the evening peak hours. And I think it's from the average between something like 4 p.m. and 10 p.m. I can't remember the exact number now. And as you might expect, the rural residents and suburbanites lead, and you might be thinking that's because they've got higher adoption, but actually in this scenario, the adoption by the end of the chart there, the penetration is actually rather similar between them, because this is the parity example. And so what we actually see is that even when you've got similar levels of adoption, those groups tend to drive the higher peak demand, and they're doing that partly because they drive further, which means they've got more charging to do, and therefore you get more coincident charging. There's more overlapping of charging events, which pushes up the diversified demand. And our sort of lower income social groups have less impact on peak demand. So that begs the question, who pays for system reinforcement, and how do we make that fair? Because at the moment that's sort of spread pretty evenly across everyone. And then if we sort of drill into that with a bit more detail, what we can look at the trading periods, and I've actually averaged these, so these are kind of hourly periods really, and it's an average of weekday demand. And looking at our rural residents, they've got quite a high peak in the sort of early mid-evening. It's about 6:30 where their peak is occurring. So it's after the main system peak, but it is quite a significant peak, and it is in the area where you're likely to have the weakest grids. So it's potentially an issue. If we then look at our multicultural Mets, so these are city dwellers, they have quite an interesting profile.
5 minutes remaining, Rachel.
Yeah, okay. They tend to charge later in the evening, which is quite interesting because you could imagine that city networks are designed for high peak day loads from commercial systems. So actually, it's probably not likely to be a major issue in those locations. And then our suburbanites have a rather similar profile to rural residents. You can see it's actually a little bit earlier, and that's because they're not travelling so far, so they arrive home a bit earlier. And the peak is a bit lower again because it's not so much coincident charging, but they are nevertheless having quite a big impact. But then finally, here's our constrained city group who have a much flatter charging demand. Of course, that's partly because this is looking at residential demand, and many of those don't have home chargers. So we have to ask ourselves, where is that charging occurring? But they're certainly not impacting on peak demand, really. And that does sort of come to my conclusions. So finish just by saying that I think the agent-based approach can generate some pretty realistic powertrain adoption forecasts and some quite granular data regarding charging. We can drill into sort of social and geographical categories and income bands in it, which produces quite a lot of interesting analysis. And looking at this sort of social equity perspective, so before that, these early tax and capital cost subsidies generally benefit the rich, but they're also enabling the transition. So we have to sort of balance those two things. Our social groupings have quite different impacts on electricity distribution network. And we can see that the lower income groups do not impose as much network stress as the high income groups. So that sort of begs the question about whether we need to look at how we charge, and do we need to look at, for example, more demand charging? How do we modify it to deliver a more equitable outcome in the future? And that's it, thanks.
Thank you, Rachel. I'll now open up questions to the floor. So I can start with one. Okay. When sort of people choose to purchase electric vehicles, how much do they put in their sort of thought process, if you know, generally how sort of environmentally friendly battery technologies are? Because it's clear that carbon dioxide is offset from the locality where the car is, but how much do you think the general public who are interested in EVs consider the life cycle of lithium-ion batteries and what happens to it after it gets discarded or it's not used anymore?
That is a question that crops up quite frequently on sort of discussions, and I keep an eye on these sort of social media groups, and I look at non-EV owner groups as well, and how they are responding, and those questions do crop up, but usually they they assume that they're dreadful for the environment and worse than ICE cars, and it's a way of avoiding having to think about it, really. And I think at the moment, certainly in the UK environment, EVs do provide a very good environmental benefit, pretty much regardless of where the battery is made, actually. But as we go forward, I think those things will become more important. So in my model, I do model people's greenness. That is a kind of factor in how they evaluate it. And I have looked at how changing in some more recent work, I've looked at how trying to increase people's greenness, if you like, their environmental concern affects adoption rates. What I haven't looked at is that kind of level of detail about how they might consider the embodied carbon in the battery specifically. Although I do have some data that looks at how total emissions fall over time, taking into account the embodied carbon. So I have sort of started to look at it, but not in that kind of level of detail, I don't think.
Okay, thanks for that, Rachel. There's another question just come in from Robin Idle Enthovens. Is vehicle life expected to be the same for EVs, or will there be re-equipping or upgrading of cars beyond the life of the first battery life, increasing availability?
I think historically, that's perhaps what people thought and actually do. So, if you had an old 24 kilowatt hour Leaf, the battery might well expire before the end of the car. And you do see people offering battery upgrades to Leafs to go up to 40 kilowatt hours, or I've even seen them up to 60 kilowatt hours. But actually, I think with the new generation that are coming forward that have ranges of 200 plus miles, if they're going to do 1,000 cycles, let's say the car is going to do 200,000 miles. I suspect the battery will outlast the car, and it will be more a case of the car gets scrapped and the battery gets used in second life for home storage. Does that answer that question?
Yes, I believe so.
Okay.
Okay. There's another question just come in from Alan Dunbar. How big an impact will concern about battery life have on second-hand value and therefore uptake from the late or low price point adopters?
I think that's an important question. And that's really about sort of depreciation rates on cars. How much are they going to be worth? At the moment, the way that lease companies are valuing them, which is quite a good indication, is that they don't think that's going to be a big problem, I don't think. And that is sort of backed up, really. There's quite a lot of data, public data out there now about the lifetime of batteries. Obviously, you'll always get the stories about those that failed, and those in quite difficult environmental conditions, which has happened with some of the first Leafs, for example, that came out being operated in very cold environments. But I think we're now seeing that some of the early Teslas have done 300, 400,000 miles that are being used for taxis and things like that. There are people who've done 150,000 miles on the original battery in their 80-mile range Leaf. So I think as time goes by, we're probably going to see less of an issue there. I think we'll see that they retain their value quite well, actually.
Okay, thanks for that, Rachel. I think I'll close the questions for this talk, and in the interest of time, invite our next speaker, Charlie McKinley. So thank you again, Rachel.
Okay, thank you.
So next is Charlie McKinley from our own CDT for Energy Storage from the University of Southampton, and he'll be giving a talk on fuel cells for shipping.
Okay, so thanks for the introduction, Max. Some of you may be looking at that title and thinking, I thought this was an energy storage conference. Why is this guy talking about shipping? Well, I think my work lies towards the applications end of the energy storage and its applications brief. My PhD looks at looking at ways to introduce future fuels and fuel cells into long-range international shipping, And my name is Charlie McKinley, and my research is sponsored by Shell Shipping and Maritime. I'm going to speak to you a bit today about a concept that we've been working on. This is relatively recently, looking at trying to use integrated fuel cells to meet the onboard auxiliary demand of existing operating ships. So I'm going to give you a bit of a background on this topic. I'm going to speak to you why we're interested in fuel cells, explain exactly what I mean by this auxiliary demand, then talk to you a bit about the aims and objectives and methods used in this project, and then we can have a bit of a discussion about the results. So shipping. International shipping currently accounts for 2 to 3% of global greenhouse gas emissions, which is quite a considerable amount. In order to try and handle this, a lot of organizations have set targets. For example, the IMO targets a 50% reduction on all shipping emissions by 2050 compared to 2008 levels. There's a few challenges with this though. The pathway towards the decarbonisation is not clear. One of the issues is that ships tend to have a long lifespan of 20 to 30 years or even more. So really we need to be designing these ships of the future now if we're going to have a chance of meeting some of these targets. Some of my earlier work looked at trying to identify what the main candidates are to be the future propulsion systems for these ships, and main future fuels were outlined as hydrogen, ammonia or methanol. But I think in order to meet these targets, then it's not just going to be enough to new build ships that have zero emissions. We need to find a way of trying to decarbonize the existing fleet at the moment. Now, fuel cells are a device that converts chemical energy into electricity. One of the main advantages of these is they're relatively efficient. They can reach efficiencies up to 60–65% compared to the internal combustion engine, which tends to be around 20 to 40%. And of the three fuels that I outlined previously, hydrogen, ammonia and methanol, one of the main advantages of these fuels is that they can all be fed through a fuel cell. Fuel cells also produce very low emissions, but they do produce an electrical output. Now, there are ships that operate with an electrical drivetrain, and it is actually considered quite well understood. But if we're talking about trying to decarbonize the existing fleets, then trying to retrofit a ship that runs off combustion to run off completely electricity would be quite a big challenge, and I'm not sure if it's really feasible at this stage. Another point I wanted to make about fuel cells is they can only really reach this high efficiency if they operate in a constant maximum output. If you drop below the maximum power output, then the efficiency can drop quite considerably. There are several possible candidates for types of fuel cells that we could use in ships. For this particular project, I've modeled a hydrogen proton exchange membrane fuel cell, but I do believe the results from this study are comparable to other fuel cell types. Now, auxiliary services, auxiliary demand, hotel load, these are all terms for all of the energy demand on board a ship that doesn't go directly to propulsion. For example, major loads include compressors, pumps, heating and cooling. And the main thing about these is that they do tend to actually have an electrical demand. Therefore, this is why we're interested in them in the context of fuel cells. So the main idea behind this piece of work was to look and try and analyze whether we could retrofit hydrogen fuel cells onto existing operating large-scale ships in order to try and decarbonize some of the energy demand of the auxiliary services. And in order to do that, I've used some data that was provided from Shell. It's from a large vessel to analyze its historical auxiliary demand, then try to size and figure out what kind of scale fuel cell and hydrogen we might need on board. And then I've simulated what the output of these different setups might be on a voyage by voyage basis, and also tried to outline some key opportunities and technical challenges. So as I said, the ship itself actually happened to be an LNG tanker, which is a relatively large ship, and we've considered the ship to have a typical operating patterns of a large ship. So the results from this study should be not only comparable to other tankers, but also other large vessels such as container ships. It's possible by looking at the data to break down the usage of this ship into 33 different voyages over a 12-month period. In other words, this was 33 separate opportunities to refuel. For the purpose of this case study, I've assumed that hydrogen refueling would be available in every single one of those ports. Obviously, that wouldn't be the case in the short term and might take a while to develop that. So it's important that any concept we put forward should be capable of operating without access to hydrogen for a long period of time. But for the purpose of this exercise, I've assumed that supply would be there. This fuel in particular actually currently runs off 3 separate fuels, which is liquefied natural gas, heavy fuel oil, and marine diesel oil. And the simulations that I wrote were in Python. So to give us a bit of a background of what kind of scale we're dealing with here, the total energy demand of the entire ship for the whole 12-month period was around about 162 gigawatt hours. You can see there, then broken that down into what went into propulsion and what went into auxiliary demand. So you can see the auxiliary load there actually makes up around 20% of the total demand, which is quite a sizable amount. It's certainly not negligible. For this particular investigation, we've decided to focus on looking at the auxiliary demand of the ship whilst the ship is in transit, i.e. when it's not in port. And there's a couple of reasons for that. First of all, when it's in port, that's when we're going to be wanting to refuel the hydrogen, so we might not necessarily have access to it at that time. And there may be better options for meeting the auxiliary load when in port, such as cold ironing, which is where you basically plug the ship into the local national grid. The next step of this investigation was to try to look at what size fuel cell we want to put on board in terms of the capacity. So you can see here on the left-hand side, I've looked at each individual voyage and looked at the maximum auxiliary power demand at any point along that voyage. So you can see here, a lot of these are around the 7 megawatt mark. But then when we actually looked at the amount of time that the load was at this figure of 7 megawatts, so you can see on the right-hand side, it's actually a minimal amount of time that you're at these higher numbers. So probably a fuel cell around 5 or 5.5 megawatts would be sufficient, assuming that you had a way of meeting the peaks in demand. For this exercise, we've assumed that the peaks in demand would be met by the existing fuel cell system, the existing fossil fuel system that's on board that they use currently. The next step was to try and gauge how much hydrogen we'd want to store on board. So I looked at the total auxiliary demand power for each individual voyage. You can see plotted here, and it's observable here that there's quite a lot of range, different size from voyage to voyage. This is largely down to the length and duration of the voyage itself. I could then from that try to calculate how much hydrogen we'd want. So on the left-hand axis, you can see here what the equivalent weight of hydrogen would be. And then on the right-hand side, I've tried to show the volume required in terms of compressed hydrogen. Obviously, these volumes would be lower if we use liquid hydrogen, but liquid hydrogen is quite difficult to store and requires very low temperatures. So if we're only trying to meet the auxiliary demand, probably compressed hydrogen would be easier for the short term. And then to put that into a bit of context, on the far right axis, I've shown—
5 minutes left, Charlie.
Sorry?
5 minutes left.
5 minutes left. Okay, I'll try and hurry up. So the far right axis, I've tried to show exactly how much this equivalent would be in terms of 40-foot containers of hydrogen, to put it into a shipping context. And for this particular case study, we decided to pick 10 containers worth of compressed hydrogen as quite a modest starting point to see how far that would go. As you can see, it won't meet all of the demand for all of the voyages, but it would be a starting point. I then tried to look at the demand profiles of the individual voyages. So on the left-hand side, we have the longest voyage, which is about 27 days. And you can see here, and then I've tried to model what the output would have been for a 1 megawatt fuel cell and for a 5 megawatt fuel cell. You can see here the 1 megawatt fuel cell acts as a base load and actually would have used up 99.5% of all the hydrogen. So this would be preferable here because there are times with the 5 megawatt fuel cell where the fuel cell output actually exceeds the demand. So in this case, it may have just been lost energy. Whereas for a median length voyage, about 8 or 9 days on the right-hand side here, then again, the 1 megawatt acts as a base load, but because it's a shorter journey, then by the time you get back into port, you'd still have half a tank full of hydrogen, which isn't ideal. So in that case, the 5 megawatt fuel cell would have been better. So we conclude from this that if you're doing lots of long voyages, then a smaller fuel cell would be better. And if you're doing lots of short voyages, then a larger fuel cell would be better. And obviously, if you're using a smaller fuel cell, then it's going to cost less and it's going to take up less room as well. So we could judge from this that for a given period of time, there probably would have been an ideal optimal fuel cell size for a given hydrogen capacity. So I wrote a simulation to look at these different fuel cell sizes, how much actual the fuel cell would have outputted, how much excess energy would have been lost, and therefore the total fossil fuel reduction. I won't go through this I'll try to go through this quickly, but for this given one, we can see the 3 megawatt fuel cell would have actually been optimum for this case. To put some numbers behind that, so for this case study of a 3 megawatt fuel cell and 10 containers worth of compressed hydrogen, which is quite a modest introduction, then this would have reduced, this would have outputted 10.6 gigawatt hours of the 24.4 gigawatt hours that I pointed out in an earlier slide. Therefore, we could then, based on historical fuel usage, we could compare this to the actual, to show the amount of fuel that would have been saved. And this actually would account to 2,343 tons of CO2 emission savings per year, which is quite significant, really. And as well as other emission savings, such as nitrogen oxide, sulfur oxides, and particulate matter. So to summarize, from quite a modest additions of this case study that I've simulated, we've made quite big emission savings. We've also found that if you're doing lots of long voyages, then a smaller fuel cell is preferable, and lots of shorter voyages, then a larger fuel cell is preferable for the same hydrogen capacity. Obviously, there's quite a few technical challenges with this. The hydrogen supply might not necessarily be available to begin with in the short term. Hydrogen is always tricky to store, so that's a consideration, and there would be a capital cost with this concept. But I think this would be a really good learning opportunity if this is the way the industry is going to go, and we're going to be using these ships, using fuel cells on ships in the future anyway. Then having experience of seeing handling hydrogen and seeing how fuel cells work for these large vessels would be invaluable at this stage. So I think there's some merit behind it. Okay, thank you for listening, and I'd like to hear your questions.
Thanks, Charlie. That was very good timing. I'll open the floor up for questions now. Okay, I'll start with one question. So this might be, you might see my lack of knowledge in this field here, but I was wondering, is there an option for burning hydrogen in, well, on a ship for a voyage instead of using it to produce electricity? Because I was thinking of the retrofitting, as you said, it would require a complete retrofit of the motors and the transmission, because you'd have an internal combustion engine, and so if maybe you could change less, instead of turning everything into electrical, have hydrogen to burn instead. Obviously, I don't know what the efficiency is like for hydrogen, whether that's worth it.
Yeah, it could be an option. I think they're considering using, I think, a blend of the currently used fuels, and hydrogen might be an option in the short term. The issues with burning pure hydrogen is that, say, the efficiency drops to closer to 40%. In that case, you need to store a lot more hydrogen, and hydrogen's difficult to store. So I feel like it's actually the fuel cell makes the use of hydrogen a lot more viable in terms of the amount of volume you need to store on board. Also, if you're burning pure hydrogen, then you can produce nitrogen oxides, which there are now restrictions on for the shipping industry. So there's a couple of challenges there, which we think is why we think that long term is fuel cells are the way that hydrogen is going to go, the way the shipping industry is going to go.
Yeah, that makes sense. So I've got another question from Andy Cruden. So Charlie, what is the status of demonstration of fuel cell systems on ships for either main propulsion use or auxiliary systems? Are these all hydrogen systems or reformed hydrocarbon fueled systems?
So in terms of what's out there at the minute, then there's very little examples of fuel cells being used on ships. These tend to be for short distance ferries or very small scale ships such as the Energy Observer. There's not really any demonstrations of these fuel cells being used on large scale ships, which is why we feel like this particular concept could be a kind of gateway into trying to demonstrate that.
Okay. Thank you, Charlie. I think if there are no other questions, then I will introduce our next speaker. Nope. Okay. Well, thank you very much, Charlie.
Thank you.
So our next speaker, who should have been speaking first at 10 o'clock, is Dr. Andrew Smallbone from the University of Durham, and he will be our keynote speaker for this session. So I'll pass on to you, Dr. Smallbone.
Okay, thank you very much. I hope you can hear me nice and clearly and you can see my screen. So I'm
Yes.
going to be talking a bit today about our EPSRC Network Plus and how it's relevant to you guys. I also talk a little bit about my research. My name is Andy Smallbone. I'm from Durham University and I'm an associate professor at Durham. We've basically got two Network Pluses, and I'll talk about what those are, and they're both got relevance to energy storage, and I'll introduce those first. So the first kind of question really that people say is, what on earth is a Network Plus? So a Network Plus is funded by the UK Research Councils as a platform to disseminate research outcomes from large projects, from CDTs, etc., etc. So it's a way of disseminating research across the UK in an effective way. Essentially, they fund large conferences, engagement activities, support activities, and during lockdown, we're doing a lot of webinars and so on. So we've got a dedicated team which runs these events. We're recruiting for them at the moment, but a number of them in place, and we've been running some events. So keep an eye out for that. Another role as part of that is to show some leadership around these topics and to feed kind of what's going on in research forward into UKRI and also into government, so that everyone's knowledge of the topics and the challenges around our Network Pluses are well known. So just before I say about our Network Pluses, there are other ones which cover transport, bioenergy, as well as obviously energy storage directly. The Network Pluses are supposed to be for essentially everyone, principally for researchers and academics, but also people involved from industry who are working as technology developers. They're not just for science and engineers, they're also for social scientists and people involved in economics. So it shouldn't be a closed book to anyone. And of course, we see people at our events from industry, from senior management. We feed a lot into policymakers, and so they've started attending events to find out what's going on around the state of the art. And also, I guess this is really for your supervisors. The funders are certainly watching. They're attending all of these events. They're stakeholders in terms of being members of advisory boards. So they're very much a good way of disseminating your outcomes is to put them in the Network Plus, because it goes to the funder ultimately. There's no fee So, and you don't need to sign up to be a member. You know, just come along to the events, and then you are effectively a member of the Network Plus. So now normally the events would be in person generally, but obviously in lockdown it's all online, and there's no fee whatsoever to attend events. So please do. We have 2 Network Pluses. But run by the same core team, which is one is on the decarbonisation of heating and cooling, which is an extension of the SUSTEM activities that have been going on over the last, well, up to 10 years, but maybe 8 or 9 years. And then we also have one which is focusing on transport and focusing specifically on and the challenges of hydrogen for transport applications. Across the next 4 years, that's 20 events. I'm not including online webinars in there. They're happening at the moment. There's 1 or 2 per month going on. We've got a number of national conferences, research sandpits, training and workshop events, which will all be free to attend generally. There are around 10 researcher secondment opportunities. That's specifically funded secondments from academia into industry or government, or vice versa. There are travel bursaries to support early career researchers, not PhD students, unfortunately, to attend the co-organized events. So if you haven't got a budget and can't afford to go to those events because you don't have a budget, then you could potentially apply to the network when those events were launched to have some travel covered. There is multidisciplinary research feasibility studies. So we're launching a number of calls, and those calls will be funded at the scale of about £50,000 size calls. And there'll be 16 of them across the 4 years around and usually supporting activities around the network. So for example, if the network needed to know some specific research question in order, and it was a very common question, we might fund some research where we bring a multidisciplinary group together which can answer that question. A lovely example of that is we're just funding a project at the moment on the economics of hydrogen for transport. Obviously, it's a very, very important and topical question, and that will deliver over the next 6 months an answer to that kind of question. And then finally is around our technology roadmap development and leadership of the topic. I mean, we're currently developing a hydrogen technology roadmap, and we're also developing roadmaps for different pathways to decarbonize heat and the key technologies which unlock those. And the reason we're developing those roadmaps is to communicate that up to EPSRC and the other wider research councils to say, well, what is the current state of the art in these individual areas, so we can establish and understand exactly where, you know, and push that forward, because obviously decarbonisation is such a key topic and requires a lot of new technology. The Network Plus on heating and cooling is a partnership between Durham, Oxford, Brunel, Heriot-Watt, Leeds and Northumbria. It's got a large number of partners. There's only a few on this page. There's 30 in total, and these are the kinds of people that will be talking at events. They've committed to doing that. So, and there's a huge pull in this particular area at the moment. Around the network, I guess you should think about the network. If your work is relevant to heating and cooling in any way, then it's probably relevant to you. And the way it's been shaped is to cover all aspects of that. So these are the technologies, which are called here primary engineering technologies and systems for decarbonisation. So that's the core technologies that produce the heat or the cold, or the store the heat or the cold, etc. There's the underpinning technologies, materials, control, retrofit, and infrastructure, and that's anything which unlocks those core technologies. It might be, say, a new energy storage material for a thermal storage unit. It would be that. The question around on a holistic level, you know, what's our future energy system look like, and how will that support heating and cooling, and how do we afford that, and how are the economics working alongside that? And then there's the less scientific domains, but really key and important things is one is understanding how users and social impact of changing our heating and cooling systems, how will that affect them, and how can they feed back and that information up to the or out to the engineers. And then we've got the policy side of things where obviously we're coming to terms with the idea that maybe heat will be more expensive in the future. How do we set in place the right kind of policy which will support and help roll out and manage people's expectations of that, as well as developing the leadership to help us to do the transition to net zero. Now, moving on from heating and cooling and moving to the transport side, we have a similar sized network, again, cutting across industry, academia and government on how do we roll out hydrogen for transport. This one's got 8 themes. One is, where does the energy come from for all this hydrogen and how do we get that to work? How do we produce that hydrogen? There's many ways of producing it. How do we distribute it? How do we store it on board vehicles? And how do we make that compact and lightweight? How do we convert it to electricity on the vehicle, whether that's fuel cell or internal combustion engine or another technology? What about the powertrain of the rest of the vehicle? Essentially, it's the same as an electric vehicle. So, but how does that work uniquely for hydrogen? How do we work with hydrogen in terms of its safety, the materials that are used and are needed in order to keep that safe? And then you've got kind of more transport related and specific actions, such as how does it fit within the future transport system, whether that's across multiple modes, logistics and autonomy. There's a huge opportunity for hydrogen in this space. And then, of course, how do we incentivize it through the right kind of policies? How do we understand its economics and its societal impact? So, that again cuts across every aspect of hydrogen. The most relevant to you is obviously the theme about storage. If you want more information about our 2 networks, we've basically umbrellaed them under this idea of Net Zero Research Network, which is our website, which is netzeroresearch.co.uk. If you want to sign up to attend events, or know that they're going on or whatever, just sign up there. There's a link and you can put in your email and then you'll get emails saying when they happen. Basically, at the moment, we're in lockdown, so we're getting monthly online webinars and they're advertised through the Eventbrite system. When those events are finished, we post up the videos and put them on this website. So you should be able to go back and look at the history of what's been done before. This month, perfectly timed, we have a hydrogen event on compact and lightweight storage. So yeah, if you want to find out more about that, then go to the website and then find out more. So that's about the networks. My own research activities really in energy storage, I guess, are around what I've put down here is kind of 4 areas, and I'll focus on one today rather than talk about all of them. But yeah, we're working in Durham around grid scale energy storage systems and the techno-economics of those. I'm currently building a hydrogen power to gas demonstration system in the lab. And we've been doing quite a lot of work on pumped heat energy storage, which is an electrical energy storage system where where electricity is stored in the form of heat and then recovered back to it via a heat pump engine system. And then what I'll talk about now really is some of the work we've been doing on the transport sector. So how storage and how important storage is within the integrated powertrain system, and what kind of options are out there for doing that, particularly for larger heavy duty vehicles. So this is what the inspiration for this work was that there was a ban on petrol and diesel car planned for 2035, and there was a discussion around this 2035 figure. And obviously this is a very rapidly changing thing, because in the last few months it's now gone to 2030, and from what I understand about this, it's a hugely political driven target, so it's quite possible that could again come forward again. But when we did this work, the target was 2040, in fact, loosely, and it was surprisingly put at 2035. But anyway, what we wanted to do is try and understand, if people do put a ban on petrol and diesel cars, well, what are the likely performance of those kind of cars and the different technologies at that particular moment in time? So we got a project funded by the Advanced Propulsion Centre via a grant that went to Brighton University, and we've already published this work. We published it in January last year, so exactly 12 months ago, and already by the end of the year, it had already been pushed to 2030. So thank you very much for that. But anyway, the key question was what will energy consumption and CO2 emissions be for a vehicle in the future? That was our broad question. When you look at the different kinds of vehicles that are out there, and this chart here is one that has been produced by McKinsey and Company, and they've shown, and this has been shown in different forms, but I quite like its simplicity of explaining quite a complex question about what's the right technology for me as a particular type of transport mode user. So on the bottom axis here, we've got the average miles per day for the vehicle, and then the second axis is the weight of the vehicle in tons. And it's separated into three distinct areas. The blue represents, this is probably best for battery electric vehicles. The lighter green is for fuel cell technology. And then the outer green here is for bio-derived fuels. So I guess liquid biofuels or a hydrogen-based fuel, which has been synthesized into liquid form, such as potentially ammonia or some other synthetic fuel that is currently being developed. But the kind of trajectory is that as you move from small vehicles up to very large ships, you kind of follow this line along here. You can see that there's a lot of debate really around where these lines are, and technology will dictate who is the winner here. But you can see here that whilst the blue stops here, actually it potentially could stretch all the way up to here, because you've got this second line. Similarly, the fuel cell line could stretch right down into small cars and urban mobility. But anyway, you've got this trajectory of small cars, light commercial vehicles, a very competitive space between fuel cells and fully electric mobility in the medium to cars range. This is obviously really interesting because this is where everyone makes all their money. And then as you go larger to buses, to heavy duty trucks, to trains, to aerospace, to marine shipping, it obviously transitions over to stuff which is more liquid based, I suppose, because of the costs of storing things. Anyway, the key history is really that everyone's been focusing about technology and vehicle types really in this space. And what we wanted to do was look at the potential and what are the challenges in this space here, where it is now still competitive between the different fuel types. I guess historically, this space is now starting to be won by the battery electric solution. So we wanted to look in a more interesting space up here. So what we picked was our heavy duty vehicle. And our heavy duty vehicle is one similar to this here, which has got a 7-ton mass and a 500-kilometer range. This vehicle, I suppose this is the kind of vehicle that you would get a bed delivered or furniture delivered in. So it's big enough to come down your road, big enough to deliver to your house, and not kind of something that would only exclusively run on the motorway, I guess. And obviously the trends I'm going to talk about for going forward are really become more extreme as this vehicle gets larger and heavier. The view we also took of this is that this kind of delivery or this kind of truck would still exist in 10 years' time. And it would also probably be a very similar design, because it's all about this transferring this volume of space. So you're likely to have the same aerodynamic drag, and the same vehicle cross-sectional area, and this kind of vehicle is likely to keep that over the years going forward. And as an operator, you would still want to keep as much of this range as possible. So the idea was to match the driver specification of an existing vehicle, and it would be used like a conventional vehicle. Now, taking this forward, this is quite difficult. I mean, we don't really know where technology will go. So this is really our best attempt to understand where technology is rapidly moving. I've been involved in the automotive sector for most of my career, and it's always been rapidly moving, and it's increasingly so now because there are so many more components, so many more systems which can come together to make a powertrain, and they're all now at different technology readiness levels. Difficult to compare because quite often they're different sizes, weights, and efficiencies, and so on. So from a holistic level, if you integrate all of this kind of thing together, what does that mean in terms of your vehicle? So within our model, we had to integrate different major powertrain architectures. So got conventional diesel in there, battery electric, fuel cell, and a few others as well, which are a little bit more at the lower technology readiness level. I won't really talk about them in this, but this is just an introduction really to what we did. You then got a lot of different new technologies that now go on these kind of transport systems, whether they're motors, really small sized internal combustion engines, really high efficiency ones, fuel cells running on hydrogen, power electronics, batteries, hydrogen storage, and I'm also going to say etc. because there were others that were considered as well and are all part of that. Now, what we do know about all of those systems is that they would be needed. The question is, where will they be in 2050 or 2030 and that kind of timescales? So we've taken the roadmaps which have been developed by the Advanced Propulsion Center, and those roadmaps they've been developed in conjunction essentially with many stakeholders across the UK. I guess the consensus view, they represent the consensus view about where all of these things are going to go and where they've been going. So they're a good educated guess about what kind of powertrain we will have. We've cross-referenced those as much as we could against equivalent kinds of roadmaps which have come from the US. For example, when we did the work, there was less on fuel cells in the UK, and we've taken a lot of targets that came from the US around those, for example. And some of those have been updated now, but this is the best what we had at the time. And we took those forward, and then we integrated those into the models. So as time went on, all of those things improved linearly between those target numbers. So for example, one would be on the batteries, there's a certain power density, and we're expecting power density to improve over time along the lines of what you might see from a typical technology improvement, and the same kind of things have been applied throughout, including improvements to internal combustion engine systems, which are also expected to improve too. So that's kind of around the powertrain, but also vehicles are advancing in general terms anyway. They're generally becoming more aerodynamic, better rolling resistance, and more lightweighting. And if you look at the history of them, they generally follow a linear trend of improvement as time goes on. They've all become lighter and more aerodynamic with time. So we've continued those trends, assuming that those sorts of things will happen. So a vehicle in 2020 will not be the same as one in 2035, even if it's still got the same powertrain architecture. They're all going to be improving in parallel. And then the last element to consider, which is a very difficult thing to consider, is the likely changes to the UK energy system, and to try to explore what the impact of decarbonising hydrogen and power has on outcomes. So we built a modelling framework to do that. Essentially, we built a model of a truck, and then we drove that truck all day over the same driving cycle. And that then allowed us to then work out what size motor, what size engine, what size energy storage system do we need in order to complete that journey. So it allowed us to automatically design a powertrain and size it. So that was done in a number of stages. So first was to work out how much power is required to get up the hill on the journey, how much onboard energy storage would be required to complete the journey, how big is the powertrain and storage medium that is needed to do that, then working out how heavy the system is and iterating that back through again, because obviously as the system weight is the power required is a function of the system weight. And then from that, you can then work out how much CO2 is emitted to produce the fuel that's used for that journey, and how much primary energy is required to use to do that journey. The outcomes is a lot of data, and a lot of sensitivity studies are published in the work, but the key kind of summary is really as shown. So this would be using current technology. This shows the mass of the generator and the fuel tank as well. So thinking about them as one component to do this journey. So you know, a diesel engine system is pretty light and pretty compact. So that gives us a particular size of the generator and the fuel tank. If you ran that same powertrain system on hydrogen, then you would need a lot of hydrogen storage because it's not that efficient. So you would end up with something that was about 2.5 times larger in terms of its mass. You could run the engine on other fossils. You can also obviously run it on a fuel cell here, and this is a fuel cell one at the end here. The fuel cell's got a fuel tank, much smaller fuel tank required than would be for an internal combustion engine system. Due to the better efficiency, obviously needs a battery on it. So you end up with something which is slightly heavier than a classic diesel engine system. Obviously, the battery electric system has got a very heavy battery in this context, and so ends up being quite heavy in order to deliver what's been required. You would probably, if you wanted an electric system, you would probably reduce this the journey, but nevertheless, we wanted to do an even and equal comparison. So then that then can be analysed in a lot more detail, and when we do that in the work. But one way we decided to look at this was in two terms. So the first term was in terms of the powertrain and its impact on the actual vessel or the heavy duty truck in our case. And so here we present the mass or the gravimetric density of the system and the volumetric density of the system as a whole. So that's storage and the energy conversion units. What you want really when you've got, in this corner would be heavy and bulky, and in this bottom would be lightweight and more compact. If you take existing technology, the black ones here represent fossil systems. The green ones here would be different kinds of hydrogen system. And then the orange dot is a battery electric system. What you see is, as we would all expect, you end up with a smaller, more compact system, which is fossil bias at the moment, I think, and that's the way the market shows. Nevertheless, you can see here the impact of an internal combustion system running hydrogen is obviously much higher than
just to let you know, it's 3 minutes left.
Yeah, no problem. So you can see, yeah, that's obviously a bit of an outlier, and obviously the battery electric system's got some potential to go a lot further, and I'll show you what happens next on that. The second context here is what we're describing as cost to society. So the bottom axis here is the net CO2 emissions. And then on the second axis here is the primary energy usage. So when you think about this in the terms that you obviously want things to be in the bottom corner here, lowest CO2 emissions, lowest total energy consumption. You can see some of the factors that are involved here. The hydrogen here is being produced, can be produced in lots of different ways, and as can the electricity used here can be produced in lots of different ways. In this context, the hydrogen is produced from natural gas, and there are CO2 emissions from that. So that's why that's got quite high CO2 emissions, but also it's got quite notable primary energy usage, as seen with hydrogen. Now taking the technology on forward, you can see here we've got this little box here. Actually, that's zoomed in. That's what this box is here. And what you see in 2030, if you take those assumptions, you can see the first thing is this huge convergence from the original data around volumetric and gravimetric density. You see a much more significant convergence, very, very much more closely aligned in terms of mass. In particular, there's almost a line here between these key technologies, whether they're fossil-derived hydrogen or battery electric, which is very interesting, which suggests that they're not going to be too dissimilar. The outlier really here is a hydrogen kind of internal combustion engine system. In terms of CO2 and primary energy usage, everything's come down except for the fossil stuff, and we're starting to see that emissions are lower here for the hydrogen system. But this has to be recognized that this is one pathway for hydrogen, and I'll talk about that in the next slide. Battery electrics come right down again, but again, nothing's net zero, and obviously everything is different in terms of their primary energy consumption. Now, when you think about this in terms of the net CO2 emissions, I showed those first two charts, and they were really focused around one form of hydrogen, and there are many ways to get hydrogen. And here shows some examples of different pathways to hydrogen. So the first one here is actually comparing with diesel. You've got hydrogen from gasified wood, hydrogen from natural gas, which is what we used in the previous slide.
30 seconds left.
Yeah.
Small bump.
And then we have natural gas with CCS, which is less than diesel, hydrogen from coal plus CCS, electrolysis from wind, and then we've got grid-based electrolysis, which is probably not going to be the way it is in 2030, but that's current grid. And then you can then take the same analysis and take it to electricity. We've got electric grid, we've got from nuclear, we've got offshore wind, which is shows negligible electric grid, assuming you can get it to your vehicle. And then we've got the CCS routes, plus two different pathways with very low and ultra low CO2 emissions per kilowatt hour from the grid. I think.
Sorry, I'm going to have to stop you there as we're running over time already, but I'm sure there'll be questions that we can run through quickly that you can cover your content with. Oh,
so it's not a problem. The next slide is the end slide, so I'll just finish this conclusion here.
Okay,
and then I'm done.
Not typing their questions, then I'll address them to the speaker as soon as he finishes.
Okay, so one is it's difficult to beat diesel in this context. I mean, the data shows there's a lot of energy to carry, and there's a lot of engineering required to carry that energy. So the challenge really is, how do we decarbonize power in order that we can deliver this? And of course, the obvious conclusion is nothing is net zero. So this is just a transition to whatever is going to be net zero. And that's the end of my talk. So thanks very much for listening. Please do sign up for the events, and do make sure you come along. I'm sure when there are webinars, your supervisors will be keen.
Thank you very much, Dr. Smallbone. So first question from Dermot Roberts. Why does BEV stick out on the CO2 per kilometer axis when it doesn't stick out on the joules per kilometer axis? So
yeah, there's a lot of assumptions in here. So if you go back to, so it depends primarily. So what we took for this BEV case was the electrical grid. So that was an electrical grid from a European data set, which tends to be more decarbonized, but less decarbonized than the UK, for example. So yes, it sticks out. So there's a number of parameters in there. It has good primary energy usage in general compared to the others, but yeah, it depends on the carbon intensity of your electricity and what's picked. When you're thinking about it in CO2 terms, you've got to think about it like this, because it's all going to change.
Okay, thank you. The next question is from Andy Cruden. Can I ask for a brief update on your PHES work? Is the system operating, and at what typical efficiency?
So this is a very long there's a very long answer to this question. The answer is the efficiency output from the system. We're currently writing the paper which will detail all of that. The kind of take-home answer is system was partially operating. It wasn't doing the full cycle, but the data we had has allowed us to determine what the efficiency is very, very likely to be. We've basically got every system and subsystem working, and we characterize those, and we built models of those things. So the precise number is, I think, about 63% round trip efficiency, which is something close to what was anticipated in the original design. We are halfway through the write-up of that. Well, I won't say halfway through. I would say that we're very close to submitting that. So the system did operate, but it's not carrying on as a project. So it's effectively scrapped now. So it will no longer be able to produce any more data from that.
Okay. Well, I think that covers all the questions everyone wants to ask. Just one quick one from me, if you don't mind. In the modeling part of the lorry that you did, with the weights of the diesel engine and the battery, and you've got the bar chart showing the different weights, what's the maximum payload of the lorry that you've used? Because obviously the battery took the greatest weight, but what is remaining that you can put onto the lorry to then transport?
Yeah, so we had to make some assumptions at this point here. We basically had a choice. We could either pick the base mass of the truck with nothing in it, or we could pick and put something in it and include that in it. So we could have picked either. We chose to pick just the system with nothing in the back at this moment in time. But obviously with the model, we could add on the number. I think the key thing on the trend was the more mass you put on the system, the more it moves in this direction. So it becomes more favorable to the less favorable to battery electric, I suppose, is kind of as a trend.
Okay, thank you very much for that. So I've just seen that there was another question that's for generally for Saul, Tracy, and Andy, and Andrew Cruden, sorry, and Andrew Smallbone, regarding the energy storage CDT students and whether they're engaged on the Network Plus network and on the energy storage research and innovation roadmap. There was a question of whether you were involved with this, and that the roadmap seemed to be constrained to EES and TES and didn't seem to link to hydrogen, biosynthesized zero C fuel. So I'm just announcing this question for Saul, Tracy, and Andrew Cruden, and also just because you're mentioning as well, Andrew Smallbone.
So I did see that there is a Network Plus on energy storage, and Network Plus published a roadmap for energy storage in general. I mean, we didn't feed into that itself, or I didn't. Maybe others in my team did. I don't think I did, or did indirectly. So we are within our network. We're building roadmaps for. I guess there's one roadmap we're developing which is on hydrogen in general, and that has elements of hydrogen storage within it, and also we're doing one on thermal energy storage as well. I suspect what we're tending to do is we're obviously got to take a larger holistic view, because we're looking at systems more than individual technologies. So it's likely we will adopt other kind of core outputs from other roadmaps quite readily. So I suspect they will feed into what we're doing.
Okay. Thank you very much for your presentation and for the answers, Andrew Smallbone. And with that, I don't think there are any other questions, and this is the final time, so I will close this session.